Hello, here we are again for another video. So this is performance task number 3. My name is Carl Joseph Rizal and I'm a BSECE3A student. So first is what's our topic? So our topic is about pulse width modulation. So a pulse width modulation is a digital unipolar square wave signal where the duration of the on time can be adjusted or modulated as desired. Pulse width modulation is a powerful technique for controlling analog circuits with a microcontroller's digital outputs. PWM is used in many applications, ranging from communications to power control and conversion. So we have here principle of pulse width modulation. Pulse width modulation is a modulation technique that generates variable width pulses to represent the amplitude of an analog input signal. The output switching transistor is on more of the time for a high amplitude signal and off more of the time for a low amplitude signal. So we have here the example. We have the low average voltage with narrow pulses in time in respect to time, and also we have here a high average voltage. We have wide pulses with respect to time also. The modulation of both edges doubles the information stored in the resulting pulse train, although the pulse train frequency is the same. Class AD and Class BD are the abbreviations to differentiate between two-level and three-level switching. Although the approach of synthesizing three-level waveform here differs from the method, the designation BD is kept during this fundamental analysis for coherence with previous work. So we have here the fundamental pulse width modulation scheme. We have the sampling method, the natural sampling, and PWM. We have here the two edges. We have the single-sided and double-sided. For a single-sided, we have two levels, 2, 3, and the abbreviation is NADS and NBDS. And for the edge of double-sided, we have also two levels, 2 and 3, AD and BD, and we have the abbreviation for NADD and NBDD. For today, we're gonna talk about the single-sided modulation. So we have here the single-sided modulation. Um, as we talked about last time, we have here the NBDS, which means natural sample BD single-sided modulation, and we have here NODs, natural sampling AD single-sided. So natural sampled BD single-sided modulation, or NBDS, is a simple approach to devise the DFS expression for NBDS is by simple superposition. Since NBDS can be synthesized by a 180-degree phase shift of the modulating signal to the opposing modulator. So we have here the formula. We have here F NBDS times T is equals to F nods T minus F nods pi T over 2. So subsequently, what is needed is a general expression for nodes with a phase shift modulating signal. So there's the formula for it. So the individual harmonic components are identified to be component. We have IM component MX plus minus NY, and there's the amplitude formula. And by comparing nodes at NBDS Hess plots, several important differences are observed. The Hess surface shows very pleasant spectral characteristics at lower output levels, and all high-frequency components disappear at idle. So this is the very advantage or important advantage of NBDS, whereas all harmonics of the carrier were present in nodes, especially the odd. The maximal IM component amplitudes are lower than in nodes as a consequence of the synthesis of three switching levels. So we have here the individual harmonic components are identified to be harmonics of carrier MX. We have here the formula in its amplitude. And next is the IM component MX plus minus NY. And we have here its formula also in its side. So NBDS is seen to have severe common node components around all harmonics of the switching frequency. Thus, the component mode signal is not much unlike the NADS differential signal in terms of spectral characteristics. So we have here the differential mode and the common mode of NBDS. So first is what is the common and the differential mode? So common mode and differential mode signals are associated with both op amps and interference noise in circuits. Common mode voltage gain results from the same signal being given to both the inputs of an op amp. If both signals flow in the same direction, it creates common mode interference or noise. Differential mode is the opposite of common mode in that the direction of the signals are different. So, differential mode. These signals corresponds to differential mode signals. Differential mode noise is interference in electrical equipment and measured between the line-to-line voltages and line currents. This noise is transmitted through the input lines to the utility. The stray capacitance between the circuit components and the magnetic coupling, between the circuits can generate differential mode noise. So common mode. So we have here when applying the right hand thumb rule, the magnetic fields associated with common mode signals might be opposite to each other. Common mode signals find a return path through the common ground. Parasitic capacitance between circuit components and between the components and ground are the leading cause of common mode noise in circuits. Parasitic inductance exacerbates the generation of common mode interference in circuits. So, common mode characteristics of NBDS, as it is clear from the time domain waveforms, NBDS generates a severe common mode output, whereas NADS does not generate any common mode components. A DFS expression can be derived for the output common mode signal, as here is the formula for it, and it's the other side is we have here the waveforms. The natural sampling BD single-sided NBDS. We have here the A side, B side, the difference, and the common. So next is we have here the carrier waveform, the its reference, and the control voltage of it, as you can see in our table. So frequency domain characteristics of NBDS. So as we can see here in our XM component is the normalized frequency, and in for the Y component or the Y axis here we have here the decibels. So as we can see the normalized frequency in and the its decibels. So, summary. Pulse width modulation, or PWM, is a powerful technique for controlling analog circuits with a microcontroller's digital outputs. PWM is used in many applications ranging from communications to power control and conversion. Pulse width modulation is a modulation technique that generates variable width pulses to represent the amplitude of an analog input signal. Naturally, sampled pulse width modulation (NSPWM), is the most favorable form of modulation because natural sampling does not introduce distortion or a delayed response. Next is the two types of single-sided modulation. We have here the NBDS, which means natural sample BD single-sided modulation, and NADS, which is natural sampling AD single-sided. So that would be all for today, and thank you.